And now I would like to open the first session of the conference, which is called Machine Learning for Material Science. And I'm going to give awards to Professor Yu Liu from Shanghai University with the talk Machine Learning Accelerated Multi-Component Law in Design. Professor Liu.
Okay, thank you for introduction. Can you hear me?
Yes, we can hear you. And we see the presentation.
Okay, thanks. Thanks for introduction. So first, thanks the organizer of the conference. So it's my first time to join this conference, and it seems this has a long history on the data science. So I'm very happy to have this opportunity to introduce our recent works. My title is Machine Learning Accelerated Multi-Component Alloy Design. So I'm Yi Liu from Material Genome Institute, Shanghai University, China. Okay, so it's well known the material genome approach accelerate the alloy design by applying the data science, combining with the computation and experiment. Okay, so in this talk, I will introduce two works which combine data with the computation or data with the experiment. Okay. So first part is a machine learning prediction of alloy element occupation in nickel-based superalloy. Okay. So if we look at the history of computational material science, so we can classify into 3 generations. Well, this is part of opinion from review in Nature. So first generation of computational material science is for a given structure, we calculate the energy, optimize the structure, and get the property. Okay. And for the second generation, we don't need a the structure. We only need to know the composition, and then from there we do the global structure optimization and get the structure, and then calculate the property of that structure. Just from recently, we start the third generation. So basically, it's a statistically driven design. So the starting point is chemical physical data, right? We start from that data and then do the machine learning, and then we get the composition of the design materials, and then from there we can calculate the structure and the property, etc. So basically, the starting point is data science, is data. So in the example today, so we have interest in developing the superalloy, which is turbine materials used in the jet engine. Okay, so this is the traditional nickel-based single crystal superalloy. The composition looks very complex. It has more than 10 elements. Okay, and it evolves from first generation up to second, third, even fifth. And so the key difference between each generation is the element addition. For example, starting from the second generation, so we add a ruthenium, Re, and we add more at Re at the third generation, and start to add a ruthenium, Ru from fourth generation, and add more from fifth generation. So we do have it's very important to understand how this key element affect the mechanical properties. Okay. Okay. So the workflow of machine learning based research is we need first the generated data. So in this case, we use the first principles computation to generate the data, and then we need a design descriptor or feature to describe the structure. And then we give this descriptor into the machine learning model, and then build the machine learning model for prediction. And up to this point, this is the typical process of machine learning. but as a material scientist, we also emphasize what we should do after machine learning. Okay, so we should do the learning from machine. So we need to go from machine learning to learning from machine. So it means after we build a good machine learning model, we need to do the model analysis and apply this model to understand the materials. So that's also very important. I will give the example how to do this in this talk. Okay, so first we need to do the computation to get the data. So in this case, we have a 11 ion element. This is common element in the single crystal superalloy. And we started, in this case, we started the two substitution site, okay? So either in the gamma phase or gamma prime phase, because this is the main phases in the nickel-based superalloy. And we replace the nickel aluminum with the 11 element. So there are a lot of substitution. So the combination is a huge number in principle. But so in this case, we calculate more than 400 cases. So the goal is it's not possible to exhaust all combinations of this substitution configuration. So we just do some of them. Like in this case, we calculate 400, and then we hope to build a good machine learning model to predict more substitution energy. So that will save a lot of computational cost. Okay, so that's the goal. So what we calculate is the two things. So one is the substitution energy, which is the energy change before and after substitution, and also the geometry change, how the binding, the bond length change due to the doping. Okay, so that's basically the computational property. Also is a target for the machine learning prediction. Okay. So then we need to build the features or descriptors. Okay. So our philosophy is, so we don't want to use very expensive features. Okay. So we start from very elemental properties of element or pure substance. So this is the basic elemental properties we used in this work, including the atomic weight, density, like readers, or the melting point, or bulk modulus, etc. And it's when we looking for this data, actually we get this basic properties from this website. I think many of you familiar with this. It's called the Database of Properties of Chemical Elements from Bykov Institute of Metallurgy and Material Science. Okay. So that's a starting point. So we don't need to do a lot of expensive calculation or experiment, okay, from the database. Okay, so once we have this elementary property, so we need to build the features, compound features to describe the system we have interest. So we propose the so-called center environment model. Okay, so traditionally people use the composition model. So basically just formula of the materials, okay? And then they just do the linear combination with the Moore ratio as the weight to combine this elementary properties to build a compound feature. But in this case, we know the material property is very sensitive to the structure, not just the chemical composition. So in our model, we include the structure information into the features. Okay, so we basically we define the center, the red atom here, for example, as the center atom. So this is the atom is going to be substituted. It's an ion element. Okay, and then we define the first neighbor, second neighbor as the environment atoms. So that will contribute the effect from the environment. And then we build the features, including both the center and the environment atoms. Okay. And we split our data, 400 computational data, by A2 ratio. And then we we do independent tests using the 20% of the data. Okay. Also, we do another thing. So we just train our model without the ruthenium, and then predict the property with the ruthenium. That's another thing we did. Also, we use the old data for the training and do the features selection and do the application. That's the workflow. For example, here, so if we look at we call the single substitution energy using the A2, the data set. So we try the supporting vector regression method, also the random forest. We compare these two algorithms, and this is the result. And also for the gamma phase and the gamma prime phase. So basically, in this case, for the SVR model, we get to 80, around 80 milli EV for gamma phase. Okay, so this is better. So SVR is better than the random forest, and the gamma has a better accuracy than gamma prime because gamma prime is more complex. Okay. And this is for the dual substitution energy, while roughly, again, it's 70, 80 milli EV. This is MAE. And we also calculate the bond length change, so which reflects the local distortion of the lattice. And this is very accurate. It's 10 to -3 angstrom. So this is more than enough for the structure prediction. And we also compare our performance between feature selection and without feature selection. It turns out, in this case at least, without feature selection performs better. We also try another thing. So we want to try predict the new chemistry or new alloy element, because that's important for the new alloy design. For example, we train the data without the ruthenium, and then we predict the model with the ruthenium, and to see how our model works. And turns out the error is much larger. So in this case, we go to 180 milli EV. So much larger than the previous one, which has a random split data. So that means if we predict the completely new element, if it was not seen before in the training, then the prediction is not very good. It is worse than the if it was there. Okay. And we compare if each new element or leave one out method for each new element, and then this is the result. So basically, for the transition metal, most of the transition metal, it works well, not that bad, but we have a large area for the aluminum and titanium. So the reason it can be are obvious, because the aluminum has p electrons, not like the other d electrons. And also titanium is an early transition metal, so it's different from the other transition metal. So this is the prediction, and how best we can do. So if we use all data, okay, and then actually we can reach 20 milli EV. So that's 10 or 20, even less than 10. Okay, so that's the accuracy machine learning can achieve. So it's already DFT accuracy sort of. So okay, so we can rank the importance of features using the random forest method algorithm, and when we pick the important features, and then we will do learning from machine from now to model interpretation. So one way is we just project energy, substitution energy to the substitution site, okay? And then we can find the distribution. This is one way. And also we can do this descriptor or feature energy property map. Okay, so this the upper row is DFT, the lower row is machine learning result. So first of all, they are comparable, right? It looks very similar, and then we can see for a very good pattern, for example, for the if we use the bulk modulus of environment and center, we project the energy, and we can see they have a very nice monotonic gradual change from very low to very high. Okay, and also we can find other similar this change, like if we use the valence electron of environment and a bulk modulus of center, we can see again this very monotonic gradual change pattern. So this map actually is very useful for new alloy design. We don't need to do first principle calculation. We just, because valence electrons and bulk modulus are available easily, and we can just by this trend we can predict what's the behavior of new element, something like that. So this is something we can learn from the machine learning model, which is useful. Okay. So as a short summary, so we developed this center environmental feature model and to include the local composition and structure information and make the prediction better. Okay, and this driven approach can increase the efficiency of the first principle calculation. Okay, so next part is about the experiment. Okay, so we use the machine learning to guide high throughput experiment to optimize the composition of high entropy alloy, HEA. For example, HEA is becoming very popular. So basically it contains 5 principal components. So it has a huge parameter space, okay, for the composition. Traditional method, it's not possible to study all this materials. So now we have new tools. Okay, so first tool is we have a high throughput experiment tools. So we can do we can prepare a sample with less time than before. Also, we have a machine learning prediction model. We can predict the good composition, and we do less experiment. So both actually accelerate the development of new alloy. So this workflow of our works. So basically, we have the flow of HTE, the high throughput experiment, also the flow of machine learning. Okay, so we will do the interactive, iterative development, go back and forth between HTE and the machine learning. For example, we generate it first, and then we build a machine learning model and predict what we should do next experiment. And then we update our machine learning model to have a better prediction accuracy, improve our model, and to see if it agrees with the experiment. If agree, we'll go next. If not, we just go back to do more experiment, to do more prediction. So we do this iterative optimization, and until we are satisfied with our prediction and satisfied with our property, the property of our materials, and then we can do further deeper analysis about structure and property, etc. And also we can dig out the correlation between, for example, composition and property relationship, or the descriptor or property relationship, etc. Okay, so we need to go from machine learning to learning from machine. Okay, so the experiment facility we use here is we develop, is called high throughput alloy synthesis facility. We develop in our lab from the powder dispenser to this powder mixing to pressing, and also the main equipment is electric arc melting furnace. So this we have a 32 station, so we can do 32 sample preparation one round. So increase the efficiency. Also, we can do this mosaic device, and also we have this polishing machine, etc. All these machines are multi-station, so it can overall it can accelerate 10 times at least the synthesis. Okay, so then we generate the data. So I'm not sure if I have enough time, so I go quickly to skip this unless you have question. We generate data first, and then we do several rounds. So first we do, first time we actually start from the, so we will measure the hardness as target, okay, hardness of alloy. And the first round, basically the hardness are pretty high. And the second round, actually we generate the hardness with the low, medium or low. So we want to have a data variety. So those are important for building a good model. And then we predict the new one, and we do the experiment verification, etc. Again, we start from these elemental properties, and also plus some compound features from the literature, okay, like enthalpy of mixing or entropy of mixing, etc. And then we do several algorithm and several combination between algorithm and the descriptor, and we do 10 times training and do the we generate 120 models, and then we do the statistical average and get the result, etc. So this is just sort of routine. So if we did this by traditional linear regression, we'll get actually contradictory result. So then that means the machine learning is really necessary in this case. So we do several rounds, we are improving our accuracy, and the best model is the support vector machine. So we can reach the error around 5%, 5-6%, okay? And the experiment error, the intrinsic experiment error is around 2. So we have a slightly higher than experiment error, but it's pretty good. And after we have a good machine learning model, actually the machine learning model can predict hardness of alloy very efficiently. So basically we can get the hardness of all possible combination or compositions in this system. For example, I enlarge the part of this, so we can find the trend. For example, so this curve reflects the molybdenum and tungsten effect, and we can see there's a peak. So this the curve, a curve of curve is there's an envelope of curves. So the maximum of this curve envelope actually correspond to the chromium, and this correspond to titanium, and this correspond to the cobalt. So basically, we can optimize the composition for the best target. Also, we can summarize this result and get empirical rules. And we also can do this descriptor hardness correlation map. For example, in this case, the valence electron concentration and this melting point have the can give us the prediction of the hardness. So this experiment, the middle one is machine learning, and then we use machine learning to predict all 3,000 composition. Okay, so they all look familiar, similar, and we use by such a map, we can predict hard HEA materials very quickly. For example, with the high melting point and medium valence electron concentration, for example. Something like this, we can do actually for all possible combination of the features we use. Okay, so by such a map, actually we can do very quick prediction for the new alloy. Okay, so basically this comparison between experiment and the prediction, they agree overall pretty good. Okay, so I think this is a summary. So we combine the high throughput experiment with machine learning and to accelerate the composition optimization of high entropy alloy. So basically, if we apply the HTE, high throughput experiment facility, we can accelerate the composition optimization by 10 times, for example. And we do, by machine learning, we do less experiment. So basically, in this case, we have a 20 times acceleration. If we combine these two, 10 times 20, actually we can accelerate the composition optimization by 200 times. So, okay, so MGI promise they're 2 times faster, the development, but actually we can do 2 magnitude higher than the promise. So also important to do, we need to go get the new knowledge by going from machine learning to learning from machine. Okay, there are many ways to do that. I saw some example, but there are many other ways to do this model interpretation. Okay, then it will lead to, so we start from the knowledge driven, and then now we are doing the data driven design. And after learning from machine, actually we can go back to the knowledge driven at a higher level. So that's the end of my talk. By the way, I thank my the program and my student. Okay.
Thank you, Professor Liu. Are there any questions? Okay, as long as we are waiting for the questions now, I would like to ask my question. You have said that you use a random forest. Why you have selected this method?
Okay, so we have 400 data in this case, so it's not a big data. So in such a small data problem, our experience is use either SVR or random forest, something like that. They are more effective than this neural network. So our experience is SVR and the random forest are almost always the best. So we didn't compare more than these two now. That's our experience, yes, for small data.
And I have one more question. When you were describing the results of the calculation, you were telling that the properties were changing simultaneously and smoothly. And do you put any limitations in accordance with the changes crossing of the phase boundaries depending on composition? Because as long as you cross the phase boundary between different regions of a phase diagram, then your properties cannot be more changing smoothly. They have to have a kind of a kink.
Yes.
Any limitation?
Yes. Yeah. So that's question about experiment, right? HEA. Okay. Yeah. So this is actually our first try. So we are ambitious. We try to explore all possible composition for the 5-component system. And so yes, so they in the materials they may lead to the several phases, and they may have this sudden change of properties, etc. But if that's the case, I think the machine learning can capture them if we have our training data cover this whole parameter change evenly. If we just cover the corner or a very limited region, probably that's a big problem. So we train the model at say the left corner, but we predict something completely different at the right corner, then it's not possible for machine learning. But if our training data are evenly distributed across the parameter space, if we design carefully, okay, then even there's abrupt change, that machine learning or our model may capture them. So this machine learning is good at this very nonlinear complex correlation discovery. So I think so I think that's very good question, also very challenging. I think we should be careful to design the training data to make it representative for the whole parameter space. But still, yeah. So we never know if we really cover the all features we have interest. Indeed, yeah. That the so we cannot guarantee we miss some important things. Yeah.
Okay.
Alexandra, one question, short question. Which of our known machine learning algorithms are most effective in solving material science problems? Your opinion, Professor Leo? Random forest, elastic net, support machine vectors, and so on.
Yeah.
The most effective algorithm in your tasks application?
Yeah, so according our experience, so SVR, the support vector regression or machine, SVM, and random forest, these two are most effective according to our experience. If we have a big data, many data, then we will try the neural network. That's our own experience. Yes.
Thank you. Thank you.
Okay. And I think there's one more question from Vladimir.
Thank you, presentation, Professor. I have a question. Please tell me how do you take account in your modeling the standard error of real experiment on determining different properties?
Okay, so that's a very good question. Actually, we are doing this now. So, for example, we are developing now optimizing for the copper. For the copper alloy, we need a good mechanical property and also good electron conductivity. So this is, but normally they are contradictory. If we add an ion element, we improve the mechanical property, but it's almost always reduce the electron conductivity. So then this is a good program for the machine learning. So machine learning, so there are many ways to do that. So what we are doing now is we use a Pareto front techniques. So we build a two machine learning model and use a Pareto front to balance these two models and find the optimal composition to satisfy both. So we do the Pareto front search. That will give you the balance for multiple properties. That's what we did. But also there are other ways. Yeah.
Okay, thanks.
Thank you. I see that there are no questions left. And actually, we don't have time anymore. Thank you again, Professor Liu, for a very interesting talk.
Thanks for your interest.
Yes. And now I would like to invite Nadezhda Nikolaevna Kiselyova to give from IMET of Russian Academy of Science to give a talk on machine learning applications to predict inorganic compounds, results and perspectives. Okay.
Oh, thank you. Спасибо.
Mm-hmm.
Okay. The prediction of the new compounds is the most problem of in theoretical chemistry. Machine learning method is one of the ways of solution of this problem. Next, please. Next. I will try to talk about the limitation of this method and the problems that arise when using it in inorganic chemistry. If possible, I will talk about ways to solve these problems. Depending on the target parameter nature, the most chemical tasks solved in machine learning processing can be conditionally divided into two types. Categorical property. In this case, the target parameters has a discrete nature. For example, formation of compound or space group of crystal structure and so on. Such tasks are related to machine learning or precedent-based pattern recognition task. Quantitative property. In this case, the target parameters has a presented in the form of real number. Such tasks are related to the regression estimation problem. Next slide. Like all theoretical methods, machine learning has its limitations. The main of limitation is the need for sufficient and representative set of objects for machine learning. When predicting categorical properties, it is necessary to fulfill the main hypothesis of pattern recognition, the compactness hypothesis. In machine learning application to inorganic chemistry, the fulfillment of the latter is a consequence of periodic law. When predicting quantitative properties, it is important to have statistical relationship between the target parameter and parameter of components. Next slide, please. When developing and applying machine learning method to inorganic chemistry, it should take into account the peculiarities of inorganic chemistry. And first of all, the limited volumes of training samples, periodic dependencies of tribute values on atomic number, the target dependencies on smoothness, the attribute description, large dimension in combination with the small parameter precedent for machine learning, and so on. Next slide, please. In order to form a representative training sample, it is necessary to have large and good databases on properties of inorganic substances and materials. As a rule, these databases contain raw information, and the expert assessment of its correctness falls on the specialist who trains artificial intelligence programs. The database developed in our institutes contains information on more than 85,000 inorganic substances. Databases integrated with information system developed in Russia and in Japan. An expert assessment of data correctness is greatly facilitated by the fact that our databases include about 36,000 PDF publications from which the data has been extracted. An important feature of databases of our institute is that, in contrast to existing information systems in inorganic chemistry and material science domain, their conceptual structure provides a very fast automated search for initial information for machine learning. Now, for example, it takes 1 or 2 minutes to find information about all known oxide spinets in our database phases. Such procedure for the well-known ACSD database takes several weeks of work of qualified research. Next slide. The integrated database on properties of inorganic substances material subsystem is an information component for this system for inorganic compounds computer design developed in our institute. Information analytical system for prediction of inorganic compounds categorical properties, and the system parameters of inorganic substances for prediction of quantitative properties. Next slide. Based on our experience, we will consider some of possibilities of machine learning method for solving problems in inorganic material science. Usually the problems of inorganic chemistry are connected with prediction of formation compounds. In this case, precedent-based pattern recognition methods are successfully used. The first task, which was solved by me half a century ago, was the prediction of new oxygen-3 composition compounds. One, the most effective algorithm of that time was used based on training of growing pyramidal networks, a special data structure in the computer memory, which accelerated the search for classifying regulators. Over the past years, many of these composition compounds has been obtained, and it became possible to compare our prediction with the new experimental data. From the 90 verified prediction for this composition, only 4 were not confirmed experimental. Thus, the prediction error is about 4%. Next slide. Much more often used in machine learning methods, the compounds crystal structure type prediction problem are solved. An example of such solved problems is the AB oxygen 3 composition perovskite prediction, which we carried out in 70s. Table shows the perovskite prediction comparison results with the new experimental data. From the 68 experimental verified prediction, only 12 turned out to be incorrect. Thus, the errors were about 80%. Next slide. Next slide. Naturally, this very first experiment in the machine learning method application, we are still far from the modern level. Taking into account our many years of experiments in inorganic compounds computer design, more advanced methods and programs for machine learning have been used. Now, the system for prediction of categorical compounds properties includes the most popular pattern recognition programs. The most promising means of improving prediction accuracy includes collective decision-making method. Our information analytical system developed in our institute contains several programs with such methods. Next slide. We are use other method to improve prediction accuracy, taking into account the peculiarities of an organic object. One of the most successful ways to improve the prediction accuracy in the case of samples containing several classes of objects is the multi-stage learning. For expert evaluation of data of machine learning, special programs have been developed for determined outliers in data. To fill in the gaps in the values of component properties, properties of chemical elements. Interpolation using taken into account the elements properties periodic dependencies on other elements parameters. In this case, the machine learning method application possibility was also tested for quantitative property prediction. An important subsystem of information analytical system is the program set for selecting of the most informative attributes. Next slide. It includes 3 programs based on this algorithm. In addition to the initial component parameter set, it is possible to automatically generate simple algebraic functions, which include initial parameters combination with the subsequent selection of the most informative functions. However, it should be noted that the use of only informative attributes always reduce the prediction accuracy. Next slide, please. Next slide. Well, categorical properties prediction is just a small part of the practical problems in inorganic compounds design. The majority problems are associated with the object quantitative characteristic prediction, for example, melting or boiling point, the crystal lattice parameters, band gap, critical temperature of transition to superconductant state, the electrical and mechanical properties. To solve such problems, we have developed the Paris parameters of an organic substances system, which includes specialized machine learning programs taking into account the subject area peculiarities. Now, for example, random forest rich program, Lars, and so on, from the scikit-learn package for Python language. They use regularization various methods of most important attribute selection, filtering outliers, and so on. One of the promising approaches in the machine learning method development for prediction of inorganic substances quantities properties is the compounded algorithm creation, for example, multi-level methods. Next slide. The subsystem for machine learning quality estimation in the Paris system allows to estimate the mean absolute and mean squared errors naturally in the cross-validation mode, the determination coefficients, and the classical method, the classical diagrams of deviation. These diagrams allow us to identify outliers in the experimental data. This slide illustrates this solving this problem of determination of errors in the publications. Next slide. The estimation of the crystal lattice parameters values in the combination with the space group prediction of new compounds is of great importance for subsequent quantum mechanical calculations, since it becomes possible to determine the atom arrangement in the crystal lattice. This slide shows a part of the space group prediction and lattice parameter cubic perovskite estimation. Next slide. I analyzed about 1,000 publications on the application of machine learning method in inorganic material science and inorganic materials industry and selected the most common ones. This slide shows the statistic of publication in different areas. In the field of basic material science, the largest number of articles is devoted to predicting the crystal structure of inorganic compounds, mechanical properties, and band gaps. However, the industrial application of machine learning far exceed the use of this method in science. The vast majority of articles are related to metallurgical application of machine learning. Next slide, please. Our experience and the experience of other researchers allowed us to outline the prospect for the approach development. I tried to highlight the main problems and ways to solve them. Most of them are partially solved by us or are being solved. The main problem is the representatives of data for machine learning. Only creation of databases with reliable information can provide a successful solution of this problem. The new machine learning method development taken into account the subject area specifics is the second main problem. The most promising areas are the collective decision-making method application, for example, machine learning algorithms, ensembles, multi-stage learning, and so on, as well as the combined method, for example, neural networks, deep learning, multi-level method, and so on. That's all. Next slide. So,
I thank you for a very interesting talk. Are there any questions? I probably have one question, actually a comment. It's really interesting work, and it really gives an insight of the materials modeling, especially the part concerning the data and data cleaning in a way. Do you have any particular references of the data which is reliable? I mean, any sources where you think the data was the best prepared in terms of the databases?
Our databases contain information of the different types. For example, the most large databases phases contain raw information, but in other databases, for example, databases on the properties of materials for electronics contain the expert assessed data. But the process of the search for outliers of data is a very expensive and laborious problem for estimation of data correctness. We developed the special programs for determination of outliers, and they work very well. But the problem of the assessment of correctness of data is very hard problem for the any areas of our inorganic chemistry and material science.
Okay. Any more questions? Look into the hands raised. Okay, there are no more questions. Thank you for your talk again.
I am sorry for the problem with my presentation. I am sorry.
Now I would like to invite Professor Matteo Baldoni and to give a talk on artificial intelligence, machine learning and data-enabled multi-scale simulation workflows for the design and development of molecular materials.
Hello, thank you very much for the introduction, and thank you for giving me the opportunity of speaking about my work today. Can you see the presentation?
Yes, we can. Perfect.
Screen, yeah. So I am Matteo, so I'm a part of the Diamond Lab, and sorry, this is not the right one. Yeah. And at the Diamond Lab, we do multi-scale simulation for the design and the development of molecular materials. So some general consideration about the material science discovery. So the development of breakthrough technology is related to the introduction of new materials with unprecedented properties. This process of design and validation of new materials can be tedious, time demanding, and sometimes dangerous. So we do believe, and we do have a quite long history in that computational modeling provides a promising alternative to support and to guide experimental activities. But when you need to test a lot of materials, high throughput properties valuation is usually hindered by the time-consuming electronic structure calculation. So today I'm going to show you how artificial intelligence and in particular machine learning algorithm can speed up this overall the overall process. So, of course, a lot has been done in literature in the field of material science discovery with application of machine learning to material science discovery, but most of the work has been focused on the properties of individual molecules and crystals. But we mainly focus our attention on amorphous molecular aggregates. Why? Because in our institute, the Institute for the Study of Nanostructured Materials, our experimental colleagues, they build a lot of organic-based electronic devices. So this is a thin layer amorphous molecular technology. So you do the devices are composed of a stack of molecular materials, and since this is molecular materials and they are electronic device, we are interested in the propagation of current. So the charge jumps from the localized state of each molecule from one molecule to the nearest neighbor. So the observed effective mobility of charge carrier results from the convolution of a manifold of intermolecular configuration. So in order to provide a complete simulation of the device, we require to couple these results with some higher scale simulation like kinetic Monte Carlo calculation. So this is inherently a multi-scale problem, and this is how we tackle this kind of problem. So this is kind of schematic of our general workflow. So we usually drive molecular classical molecular dynamics code in order to provide the morphology of some large realistic aggregates. We do analyze these aggregates from morphological point of view, and we do extract molecular pairs out of this configuration, and we use this as input for computing the electronic coupling parameters, which are something that are related to the flow of current in the device. And finally, we gather all of these results to provide distribution of these electronic parameters in order to scale up our simulation. But this is quite technical slide just to give you a flavor about the actual density functional based calculations. So I hope you can see my mouse pointer. So basically the point is that you have this kind of situation. You do have two molecules, one is charged, and this is the initial state. And after a jump of the charge to the nearest neighbor, we do have this movement of charge from one to another. So this is the initial state, this is the final state. And here in the center, you can see the actual shape of the singly occupied highest molecular orbital involved in this process. So what we want to do is to calculate the energy of the initial and the final state and the overlap between the two electronic states. So the point is that one will use the density functional theory for this kind of calculation, but DFT fails in describing charge transfer states, giving as a result an average between the initial and the final state. We overcome this limitation using a different implementation of density functional theory, imposing some constraint, some special constraint in the charge and spin density. So basically we can force the DFT to give us the right results in the two charge transfer states. And this is something from the past that we have done already, but there is no machine learning yet. So these are some results from what we have already published. So at the beginning, we did some tuning of the method. So we create some artificially modified configuration of molecular pairs, and we artificially move it in order to understand how the electronic coupling is influenced by the configuration of the molecular pair. So here you can see how this quantity is related to the distance between the two molecules, and really it's influenced by the rotation along some specific axis. So from this idealized structure, we go then to a more realistic sample of molecular aggregates. This is what you can get out of the molecular dynamics simulation. We do extract all the molecular pairs in several of this kind of sample. We do an analysis of their morphological and geometric configuration and calculate the electronic parameters for each couple, and then provide a distribution of these electronic, diabatic electronic coupling parameters. So in order to provide a good distribution of these electronic parameters, we need to simulate thousands of these molecular pairs. And even though our implementation is quite computationally efficient, constrained DFT simulation are relatively computationally expensive. So we need at least 4 hours for each pair on a high-end computational node. So we do believe that machine learning approach can increase dramatically the overall throughput. So we want to train our machine learning algorithms on the results obtained from constrained DFT calculation. Apart from the algorithm themselves, it was immediately clear to us that data representation is crucial for this kind of problem. Why? Because the input and somehow the output of multiscale simulation are this kind of thing. So you do have a representation of the structure in terms of a table, in which in each row you have 4 columns. The first one is about the element, keeping at a certain position, and then you have X, Y, Z coordinates of the atom. Usually this is all that you need for ab initio calculation, and this is extremely human-friendly data representation, but it's not machine-friendly at all. And on top of that, it depends on the order of atomic entries, and it's not an invariant with respect to translation and rotation. So we want to convert the feature, so the atomic coordinates, into a more machine learning compatible format. Has to be, unfortunately, still human readable because we need to modify it by hand from time to time. So we need to figure out how, what kind of intrinsic information to the system can be computed starting from the coordinates and to be injected into the machine learning algorithm. So the electronic coupling can be mapped onto a subset of the coordinates. So from the previous results, we understood that the distance between the 2 molecules is the main feature, and also the mutual orientation, but also the molecular distortion of each molecule inside the aggregate compared to an ideal structure. It can influence quite importantly the value of the electronic coupling. So we did some preliminary study using a different data structure, so the so-called Coulomb matrix as a feature. So the Coulomb matrix is basically a matrix in which in each column, in each row, you have all the elements, all the atoms in your molecule, and each element of the matrix is a ratio between the product of the charge of the atom and the distance between the atom. So this representation, this data structure intrinsically represents elements, distance, mutual rotation, and distortion of the molecules, and it proved to be quite functional. Actually, the results are not bad at all, but there are 2 main drawbacks. So this representation could be huge, even for a small molecule. DPB molecule, it's the one, this test molecule I've shown you before, it's around 100 atoms, but the Coulomb matrix, the relative Coulomb matrix has more than 10,000 elements, so it's quite heavy. And again, the Coulomb matrix depends on the order of the atoms in the source file. This is very bad for transferability of this data structure. So we made some tests and we found how best feature setup. So we can describe the distance, which is a major factor, as a scalar distance or as a vector distance, which is slightly better. Probably just because we do have, so in the vector distance, you have 3 components, so you have more degree of freedom from computational point of view. The mutual rotation of the 2 molecules in the pair can be represented with quaternions or with the rotation matrix, and we found that the rotation matrix representation is the best one. The molecular distortion, which has a small influence but is still important, is represented by RMSD, so the mean square displacement of the atomic position of the real molecule, I mean the molecule in the real aggregate compared to the molecule in its idealized geometry, optimized in vacuum. So our best feature set is the distance vector plus the rotation matrix plus the RMSD. So this was about the data structure, and I told you that this is most most important and problem that we have to analyze. But of course, algorithms are important as well. So we tested 3 models. Actually, I didn't do that, but this is the work of our new PhD student, Fabio Le Piane, who has very strong background in machine learning, and he is very helpful in this kind of situation. So he tested the random forest, a gradient boosting, and a kernel ridge regression. And he found that this is the best algorithm for our purpose. And finally, this is the preliminary results that we got very recently. As you can see on the left, there is kind of good agreement given the complexity of the system of this problem, which is kind of very demanding from structural point of view. So we have relatively small error. And this allows us to have instantaneous prediction of the electronic coupling, so we can increase a lot our overall throughput in the material discovery activities. And you can see also that the distribution of the prediction and the truth, they are very similar, which is very encouraging for us. But in order to enter a production phase in which we can analyze a large amount of new materials, a lot of improvements are needed, and this is what we are doing right now. Of course, there is a problem of data. By now, we have a small amount of data for the training of the algorithm, so we are in a phase of few shot learning. We do have to fix, to understand better the feature for the rotation, for the mutual rotation between the molecules inside the pair. So the quaternion and the rotation matrix maps the rotational space 2 times, and both of them, they are not aware about symmetry, but molecules, they do have a structural symmetry, and sometimes they do have a different symmetry in the molecular, the electronic structure. So we need to find a symmetry aware or representation of this. The distant vector that we are using is not an invariant in respect to rotation and translation. So we need to find a better representation for mutual distances. And of course, we would like to test how set up with different molecules and to see how the different elements can influence our results. So basically, this is what I had to say. And I would like to thank you, all of you, for the attention. And I would like to show you the name of the people that have been working during the years in this project. So Fabio I have already mentioned. Andrey was a former postdoc in our group who provided the molecular dynamics simulation, so the molecular aggregates. And Alessandro Pecchia, who is head of our institute, have a branch institute in Rome, and of course, Francesco Mercuri, who is the head of the lab. And again, thank you very much for the attention.
Thank you for your talk. It was very interesting. Any questions? Please raise your hand up. Okay, until we're waiting for the questions, I have a small one. You mentioned in the last slides that yes, there is a shortage of the data. What kind of a data would be the most interesting for you and, let's say, valuable? Theoretical data or the data coming from the experiments?
No, right now we are focusing on the simulated data because we want to speed up the simulated process of material discovery. And
do you use the data coming from the material, the types of the projects like material genome and etc.? The one which is carried out in Germany and in...
Yeah, of course, it would be great, but there are very few data about molecular aggregates, amorphous molecular aggregates. That's the main point. So this is a field in which not very much has been done from machine learning point of view, and there are some databases, but not as big as, for example, inorganic semiconductors. This is a niche from this point of view, somehow.
Okay, thank you. Some more questions? Okay. I don't see any questions, nor in chat, nor
Sorry. You use it by the kernel-rich programs and other programs of machine learning. Have you tried to use deep learning programs? Artificial.
We are going to do that, but by now, I think, the problem is that we don't have enough data for that, and we will have to have full control on the feature. So this is something that we are going to try in the future, of course, but we need more data, because right now we have kind of 400 couplings, and we will need much more for that.
Okay, any more questions? Okay, well, I don't see any questions. Thanks again to the speaker.
Thank you.
Thank you. And we are now moving to the next talk, which will be given by Jakob Ropers from University of Liverpool.
Hello everyone, it's Vitaliy Kurlin who will be giving this talk.
Okay. Matteo, can you switch? Oh, okay, great. Now we can share the screen.
Can you see the slides?
Yes.
Okay, very good. So thank you very much to the organizers for running this workshop. This is a joint work with several colleagues from the Materials Innovation Factory in the University of Liverpool, which is a sort of a research spin-out from the chemistry department. However, our group includes mathematicians and computer scientists, so there will be a more theoretical approach in comparison with the past talks. So I'll start with a high-level overview. So our methods apply for any periodic crystals, organic, inorganic, or metal organic frameworks. The only current restriction is periodicity. So they're all solid crystalline materials, which we will call periodic crystals, or briefly crystals. They consist of all elementary blocks. So one block is a motif of atoms or ions or molecules in a unit cell. So here in this ice cube, this cube is periodically repeated in 3 directions, and that's how we get the infinite periodic structure. Then, when mathematicians look at the problem of crystal structure prediction in particularly, then we immediately see the ambiguity problem, because the same periodic point set, and in the top row here you see simply 4 lattices. So these 4 lattices can be easily represented by infinitely many different inputs. For example, you could generate this unit square lattice by using a simple orthogonal basis, or you could take a different basis spanning a red parallelogram or a more narrow blue parallelogram, and all these bases generate exactly the same unit square lattice. In addition, we could shift our points and choose them not at corners of a unit cell, but in the centers of unit cells. However, the resulting lattice of black points looks very similar, or we could say even equivalent or identical to the previous one. In addition, we can have rotations. And then, again, our basis of a unit cell looks very different. But since we study solid crystalline materials, then these lattices should probably be considered equivalent. So I actually encourage questions during the talk, and one small question for the audience is to check whether these last 2 pictures represent equivalent lattices or different. So even professional crystallographers, when look at these 2 pictures, they sometimes struggle to see that these last 2 pictures on the top row are exactly the same unit square lattice, but only a unit cell was chosen differently in the last picture. So hopefully you could see unit squares with 4 black points in the last picture as well. So these four different pictures represent exactly the same or equivalent square lattices. When we go from lattices to a periodic point set, periodic crystal, then we have even more ambiguity. We could, for example, fix a unit cell, a lattice based on a square cell, but choose different motifs for that square cell and then get exactly the same, say up to a translation, periodic point set. So even fixing a lattice does not help here. So that's why it's important to start from the foundations. What crystals or what periodic point sets should be considered equivalent? So when we started looking at this topic, we searched through many crystallographic books, but couldn't find a proper mathematical definition. So we argue that since crystal structures are determined in a rigid form, for example, via X-ray diffraction patterns, then it's very natural to study them up to rigid motion. So rigid motion is very closely related to a slightly more general concept of an isometry. So rigid motion is any composition of translations and rotations in a three-dimensional space, for example. An isometry also includes reflections. So only for simplicity, I will talk about isometries, but if you know that two crystals are isometric, then it will be easy to distinguish them up to reflection as well. So only for simplicity, we will talk about isometry invariants. So invariants were mentioned in several talks this morning. So let me formally define it, because in mathematics, it's a very important concept in almost all branches. So an invariant, so it is a property. So it could be a number, it could be a vector, a matrix, or even more complicated object. But this invariant, so property or function, it should take the same value on all equivalent objects. So in our case, on all isometric crystals. For example, we could start from a hexagonal lattice, and this hexagonal lattice could be represented by many different unit cells. Primitive, non-primitive. But our aim is to map all these initial ambiguous inputs into one value of an invariant, because all given representations should map to the same value, then it is an invariant. And similarly for a square lattice, you could start from different representations, but an invariant should have the same value. If you use non-invariants, for example, edge length of a unit cell, then this non-invariant can easily take two different values on two crystals, and we can make no conclusion in general. So these two crystals could be still equivalent or can still be different. So that's why it's very important to use invariants. If an invariant takes different values, then our objects are certainly different. When I was given similar talks more than 2 years ago now, material scientist chemist asked me, well, how about non-invariant data, but what if you have big data? Will it help? Unfortunately not. If we have a little noise in our data, which is natural from any real measurements, then a little noise is okay. But if you have a lot of non-invariant noise, then it will be much harder to justify the method. So that's why it's important to use invariants. Right. So what invariants are known? So of course, crystallographers knew about ambiguity of a primitive cell, and we tried to find so-called canonical or reduced cell. One of the best such examples is Niglis reduced cell. However, any reduced cell, including Niglis cell, is discontinuous under small atomic perturbations, as you can see in this very simple example. Let's start from a square lattice and perturb every other point slightly, so shift it from its position to every second point. Then immediately, any primitive cell, including Niglis reduced cell, will double in size. So instead of a small square, our minimal pattern unit cell will have a double, twice larger volume, or it could even quadruple its volume. So what does it mean? It means that this reduced cell is discontinuous, unstable under any atomic, under almost any atomic vibrations. So that's why it's important not only to use invariants, but also to use continuous invariants that's change only slightly under perturbations. So it would be nice, for example, to design invariants that see a small difference between the initial unit square lattice and a slightly perturbed periodic point set. Only in this way we can continuously quantify a crystal similarity, the similarity between very similar crystals, nearly identical. So again, why is continuity important? All atoms vibrate. Of course, you know all real measurements are noisy, and the motivation from crystal structure prediction, we have too many crystals, at least too many predicted crystals. So very briefly, crystal structure prediction aims to discover crystals, simulate them on the computer, and usually they start from almost random configurations of molecules put and almost random positions in a random unit cell, only making sure that they do not overlap, and then they perturb the positions to minimize the complicated energy function. So usually the lattice energy function, which we will discuss later in this talk. And this approach in crystal structure prediction leads to the so-called embarrassment of over-prediction, which is the term coined by Professor Sally Price when I talked to her personally. So she simply said that all many state-of-the-art crystal structure prediction tools, they output too many predictions, which approximate local minima of this complicated energy function. So of course, if we rerun our prediction algorithm many times, then inevitably we can easily finish close to the same local minimum, but coming from different directions. So that's why, for example, in this plot from the Nature paper by our colleagues in the Liverpool Materials Innovation Factory, you see almost 6,000 predicted crystals based on the T2 molecule from the previous slide, but only 5 actually were physically synthesized in the lab. And in this plot, each crystal is represented by only 2 numbers, density and lattice energy on the vertical axis. So of course, these 2 numbers are too simple and insufficient to guarantee a crystal similarity. So many crystals here look very similar, nearly identical, but only because the density and energies are similar, not necessarily crystal structures. That's why we need more invariants, so better tools. What are other tools we used? For example, the well-known visualization program Mercury, for example, computes RMSD, which was again mentioned in previous talks, root mean square deviation. So the key problem with RMSD, at least in the implementation by Mercury, it's an output of an algorithm. So I actually struggled to give a definition. Briefly, it measures the deviation between n matched atoms. But the key difficulty is here how to match these atoms. So Mercury by default tries to match up to 15 molecules, but again, this choice is not guaranteed, so it's not unique. So if we perturb our crystal, then choices could be different. There are also tolerances for distances, angles. So there is dependence on many parameters, and this small table at the bottom shows that if we increase the number of maximum matched molecules, then this RMSD value simply grow irregularly, and it's not clear what value to take as a distance. And actually, if you consider RMSD as a distance, it fails the triangle axiom that should be satisfied for all crystals ABC, but we have checked on experimental crystals, so on many triples, this triangle axiom fails. What are other methods? So let me first show the experimental comparison calculation of RMSD. So in this plot, every small square represents a pairwise comparison. On the horizontal axis, you see the RMSD value, so comparison for 2 crystals taken from that large T2 dataset mentioned previously. And on the vertical axis, it's the absolute value of difference of energies between the same 2 crystals. And it is easy to see that on the vertical axis, we have many pairs of crystals when RMSD is exactly 0, so really 0, but energy values are different. So it means that energy is simply discontinuous on RMSD. If you perturb only slightly, the energy can change largely. So other tools, powder X-ray diffraction pattern. So we have useful implementation by the Cambridge Structural Database Python API. On the horizontal axis, similarly, you see 1 minus PXRD similarity. So value 0 here means that crystals are very similar. So PXRD is slightly better than RMSD. So there is a smaller number of crystals when PXRD doesn't distinguish them, but energies are different. But nonetheless, it also seems discontinuous. So small values, very small differences, as you see, in PXRD similarity leads to large differences in energy. So that's why we kept looking and designing new invariants, distance-based invariants in this case. And indeed, distances were mentioned in several past talks as good invariants of periodic structures. So that's a formal definition of the average minimum distance. We start from a periodic point set. And for every point Pi, we look at distances to its neighbors. First neighbor, second neighbor, and so on. So in the first picture, you see the square lattice. So the first neighbor of the origin has distance 1, and similarly, we have actually 4 neighbors at distance 1. When we have 4 neighbors, diagonal points at distance √2, 4 neighbors at distance 2, and so on. For the hexagonal lattice, these distances are similarly increasing, but differently. Right. To avoid the dependence on any order of points, one way is to average, is to take the average over all motive points in a given unit cell. So the last picture shows a less trivial example when we have not a lattice, but a periodic point set with 2 points in this unit cell, a parallelogram. So we take the average over 2 points in this particular case. So when we average, it might seem that we lose some information, indeed. So that's why we have actually a strong invariant called pointwise distance distribution, which doesn't average over motive points. But today I focus on the simpler AMD because the average minimum distance is a vector of numbers. So it's AMD1, AMD2, and so on, up to a given number k of neighbors. And this number k is a parameter. However, when we increase k, we don't change any previous values of the AMD invariant. So this k can be considered as an order of approximation, or the number of decimal points on your calculator. So you could compute up to 2 decimal points or up to 100. So you simply make better predictions. Right. So this slide shows experimental computations for 9 experimental crystals, and let me go quickly to continuity statement. So you see when we change, when the difference between AMD vectors changes slightly, when the energy changes slightly, and this picture is very different from the previous one when we considered RMSD and powder X-ray diffraction patterns. This is the final slide showing the energy predictions based on AMD invariants, and you see the dependence on K is not really important. So in almost all cases, our mean absolute error is very close to 5 kilojoules per mole. And I should finish with the following summary. So you have noticed that we considered only points and no chemical information at all. So that's the key idea of periodic geometry. So a new area looking at crystal structures from a pure geometric point of view. And this periodic geometry approach has already found interesting cases in the Cambridge Structural Database. So we detected 5 pairs. So this is one example where geometry was exactly the same, but chemistry was different. So all crystallographers told us that this is impossible, and indeed with CCDC is now investigating for this case. Am I on time?
Okay, thank you for your talk, Vitaliy. We have some time for a very short question. Are there any questions? Okay, let me see.
Sure.
Any questions? Okay, if that is not the case, I'd like to thank you for your talk again. And now
Okay, you're welcome. Thank you.
Yeah, and maybe some questions will appear during a coffee break in Rwanda. Now we are moving to the next talk, which will be given by Professor Faridun Jalolov from Skolkovo Institute of Science and Technology. And it will be about simulation of mechanical properties of materials by using machine learning interatomic potentials. Okay, you're welcome.
Yes, thank you for introducing, and let me share my screen firstly. Yes, yeah, I hope you see my screen.
Yes, we see it.
Okay. Hello everyone, and I'm Faridun Jalolov, second year master student in Skolkovo Institute of Science and Technology. And as was mentioned, the topic of speech is simulations of mechanical property of materials by using machine learning interatomic potentials. The material can be called the super hard if its weaker hardness more than 40 GPa. Here there are some examples of hard and super hard materials, such as cubic diamond and cubic boron nitride, and also some carbide, nitrides, and borate, some of transition metals. But most of them are high pressure phases, like diamond and cubic boron nitride. And for other ones, for producing other ones like tungsten carbide, we don't need to high pressures. We need high temperatures. This is advantages, but disadvantage is a very low weaker hardness in these materials. But there are also really some classes of materials which possess really high weaker hardness, and perspectives of uses these materials very high, and it's important to develop new types of these materials of this class. Due to their unique properties, they are high hardness and also high melting temperature. The super hard materials are widely used in many industrial applications, like stamping and cutting tools, and drilling equipments, and also uses in spacecraft. For example, in this drilling equipment, which is need to produce the oil, usually use polycrystalline diamond or cubic boron nitride, or a mixture of them. And the main direction of developments in this field of technology is a replacement of traditional expensive materials by new ones with improved properties. And due to the fact that most synthesis of new materials are polycrystallines or multi-phase materials, there is need to create some methods that can describe of mechanical properties of such complex system with high accuracy. And of course, existing quantum mechanical methods are expensive and not able to describe such large systems. Also, they have a good accuracy. And also we have classical empirical methods are able to describe such systems, but the accuracy of calculation is rather low. Moreover, in polycrystals, there is an interface between grains that does not have a crystalline structure, and describing exactly the grain boundary is a difficult task for empirical potentials. And to solve this problem in our project, we performed the development of an automatic algorithm for calculating the main mechanical properties of polycrystalline materials where the interatomic interaction will be described by machine learning interatomic potentials. We employ the moment tensor potentials as a model for approximation of density functional theory calculated energy, and the MTP moment tensor potentials are based on a representation of atomic environments as a tensor of inertia of different ranks, in practice usually fifth rank, multiplying by a radial polynomial function. And the main goal to estimate the set of parameters which define the form of moment tensor potential as a function of training set. And the training of the MTPs can be done by solving the minimization problem. This type of potential accounts for local atomic arrangement and expands to the total configuration energy into the sum of contribution of individual atomic environment. And we can also call this atomic neighborhood. And each neighborhood contribution is expanded through the set of basis function. When fitting to the energy values, we need to solve the overdetermined system of linear equations, and each equation of this system is produced by the certain configuration, and it can be called the active learning set. In active learning technique, we have to provide some parameter which calls the extrapolation grade, and it is mathematically can be shown that the moment tensor potential extrapolates if this parameter more than one, and interpolate otherwise. And in practical simulations with machine learning interatomic potential code, we use the so-called two-threshold scheme, which is illustrated here. And in this scheme, we choose some two thresholds. And first threshold beyond which we select a configuration for training, and second threshold beyond which we terminate the simulation. And here you can see the active learning procedure for the single crystals. We perform this for some hard and super hard materials like silicon, diamond, and for some carbides. For this, firstly, we performed the ab initio molecular dynamic as implemented in WASP to get the initial active training set, and trained moment tensor potential on this training set. After we perform the classical molecular dynamic with this potential, with sampling, with active selection of the extrapolation configurations, and get sampled configurations which further for this configuration we perform energy force calculations and add for our training set and retrain our moment tensor potential. And each iteration in this scheme can expand the learning area and improve our stability of our moment tensor potential. The simulation takes longer without completing the extrapolations, and iterations continue until the simulation is complete without exceeding the critical value of this threshold. Here you can see the procedure of the active learning for the polycrystals. In this case, initial active training set, we use training set which was obtained for the single crystal. And we will add some extracted atomic environments in the polycrystalline with the highest extrapolative price to our training set and improve and obtain our moment tensor potentials for polycrystals. Here you can see the how the active learning set, active learning technique can optimize and improve our results. Here shown the elastic constants with potentials trained with machine learning, interatomic potentials with passive learning and active learning. And as you can see, the machine learning interatomic potential with active learning shows better results, but in terms of in good agreement with experimental results. Here you can see the results of calculation of elastic constants for cubic silicon in comparison with some another method like a TFT by using empirical test of potentials and also machine learning interatomic potentials with active learning and experimental results. And as you can see, in this case, also the machine learning interatomic potential show good results. Here results for the 3-layered cubic silicon carbide with comparison with DFT also and empirical test of potential and machine learning interatomic potential with active learning. And as you can see, in this case, the machine learning interatomic potentials also shown the best results. Here for another phase of the silicon carbide, and here the results of calculation of elastic constants for the one of the most hard materials, tungsten carbide. And here you can see elastic constants and elastic modeling, and by using different methods like DFT and machine learning interatomic potentials with comparison with experiment. And the last material, it is a tetraboride of chromium, one of the hardest borides. And here you can see the comparison of calculated TFT and machine learning interatomic potentials with experiment and with theoretical calculations from literature. And also here machine learning interatomic potentials shows results in good agreement with DFT and experiment. And in conclusions, we can say that among the used calculation methods, the machine learning interatomic potentials with active learning can optimize our results of elastic tensor calculations and show best results for monocrystals for now. And developed tested some algorithm for calculating the elastic constants and elastic modeling for the single crystals. And the future prospects can be expanding the MLIPs for the polycrystals. Thank you for your attention. Any questions?
Thank you. Any questions? Okay. Irina, do you see any questions coming? Vladimir, any questions? Okay. I see the question from Andrey Fionov.
Yes. I would like to thank you, first of all, for this interesting introduction and this information about the model for the structure of material. I would like to ask if it is possible to make the models for ferrum-based materials like rails?
You mean ferrum alloys?
Yes, exactly.
Yes, yes, it's possible to some multi-phase materials for alloys, for polycrystallines, and etc.
Is there any research in this respect? Probably there might be usage of the carbon to put into this ferrum structure to make it harder.
Yes, right now in the Skoltech, in the Chape's group, which developed this machine learning iterative potential code, they are right now working on it. They they construct some alloys and develop some potential for this, and they use these potentials. Different potentials and different models. But in our case, we constructed only the polycrystals, and we are right now developing potential for polycrystallines. But yes, it's possible develop also for alloys, some composite materials also.
I would like to introduce the next speaker, Johan Bratberg, Vice President from Thermo-Calc Software AB, and the sponsor of our conference today, which we are carrying now. Johan, you're welcome.
Okay, thank you very much for the introduction. So my name is Johan Bratberg. I work for Thermo-Calc Software based in Stockholm, Sweden. So I will base my presentation a little bit around giving a short introduction of Thermo-Calc Software, what we're doing. Then I also will discuss the materials data challenge that we see it, and also discuss processing and refinement of data using the so-called CALFAD method. Then I will also exemplify the use of the CALFAD toolbox for designing new materials and so on. So our mission is to develop computational tools which allow engineers and material researchers to generate the materials data that they need in their daily decision to drive innovation and improve performance and so on. And today we actually have over 1,600 customer sites in more than 70 different countries. And our base is, of course, the academia. We ourselves spring off from academia. But we, of course, also have a lot of research institutes, governmental labs as users. And we have also seen more and more industry users applying these kind of tools nowadays. So today we have a team of 53 employees distributed in different countries. And we also have local partners in different countries. For example, Russia, we have a local partner, Scandia Trade, based in Moscow. We have definitely seen a booming usage of this technology. So CALFAD is the methodology behind it. That's the red line. This is actually citations in the research articles published in different scientific journals. And then the blue line is the Thermo-Calc citations. So we can definitely see that's the last 10, 15 years, it has been a steep increase using these kind of tools in research. And why is that? I guess it's a lot of different reasons behind that, but some of the biggest benefits is that you can generate accurate computational materials data. In other words, you can fill in data gaps without resorting to costly, time-consuming experiments. And doing that, you will of course accelerate time to market while you're reducing the cost, and you don't actually exclude the experiment work needed, but you kind of tailor your experimental work that you need to do. It could also be to improve materials and processing conditions, of course, by understanding how they influence the final result of your products, the properties. Analyze breaks in production chains, of course, identify why, where, and when these breaks occurs. It could also be to improve the environmental and ethical conditions, for example, to understand how to substitute harmful materials or harmful elements, for example. Just a brief product overview. Thermo-Calc itself is a base product, and that you can do a lot of thermodynamic properties and phase equilibrium calculations, but it also include a data optimization module, and it also include what we call property model calculator framework, where we provide a lot of property models, but the user can plug in their own property models as well, and use the data that we can generate to feed those models. And we of course we offer a lot of different databases, thermodynamic, kinetic, and property databases. We have different add-on modules for kinetic modules. Diffusion simulations can be done with Dictra, and we also have a precipitation module, TC-Prisma. Then we also have software development kits, that is programming interfaces, which is linking the usage of our tools to your own tools, for example. We have 3 ones. TC Python is the most popular one. We have TQ interface and also TC Toolbox for MATLAB. We also offer what we call process structure and property model libraries for materials design. And here we have a steel library out already, and now in December we will release another one for nickel. I will show you a little bit more about the steel library later on. And we also have one application module which is specific for process metallurgy for steel simulations. And of course, I mentioned we have a lot of different databases for thermodynamic, kinetic, and properties, and we have them available for all these major alloy systems, as you can see on the screen. We also have it for high entropy alloys, copper alloys, and so on. So just some brief words what you can do with Thermo-Calc. So you actually do calculations for a given thermodynamic system. So you can predict amounts and composition of phases, transformation temperatures, for example, solubility limits, and so on. And you can also predict a wide range of materials property data. It could be thermophysical properties. It could also be kinetic properties. We also have some mechanical properties such as yield strength and hardness. But it could also be properties related to equilibrium and non-equilibrium solidification, using the Scheil module, for example, inside Thermo-Calc. Using the kinetic modules, Dictra and TC-Prisma, one can simulate the evolution of microstructural aspects as function of time. That could be microsegregation during solidification, could be homogenizations, for example, allotropic phase transformations, could be interdiffusion in compounds as if you have a coating systems, for example, or dissimilar joints, and so on. Using TC-Prisma, you can also predict the concurrent nucleation, growth, dissolution, and coarsening of precipitates, and also predict the temporal evolution of particle size distribution, and also get the average particle radius and number density, volume fraction, and compositions of the precipitates. And based on all this Kalfa data, we can also make further prediction using property data, property models, which is physically based models. So the picture here actually shows how it looks inside. It's a screenshot of using Thermo-Calc. If you go to this property model calculator, it will populate a lot of different models, and then you can actually decide which one you want to use and feed it with the composition and temperature and so on. And then you have different calculations type that you can do. You can do like single points or a step along and variable, or do a grid calculations. You can even do some kind of mean max calculations, including this uncertainty range in elements and so on. And we also have a batch function. If you have 1,000 of calculations, for example, you can set it up as a batch. And using the TC Python programming interface, you can actually develop your own model and plug it into this framework. And that means that then you can use all the plotting functionalities inside Thermo-Calc. And all these kind of calculations type, of course, as well. So these kind of process structured models, as we call them, they of course, as you can see to the right, the blue arrow, it increased in complexity. If you're going down, you can start with equilibrium calculations, for example, to predict phase fractions and compositions. Then you can use a child solidification model. Then you will have a non-equilibrium phase fraction and compositions. The diffusion module, then you will have add the size into it as well. Precipitation module, you will be able to add on size distribution as well, and then you finally have a phase wheel approach where you also can do the morphology, and then it starts to be more and more complex. And this figure actually shows a CCT diagram calculated using this steel library. So there you can actually predict martensites, temperatures, and fractions, perlite and bainite transformations from austenite. Okay, so I will talk a little bit more about data and what kind of data is available. And I will start with this kind of buzzword in Industry 4.0, which is actually related to data, or the integration of data related to artificial intelligence, machinery and communication, to create an efficient industrial ecosystem that is not just automated but also intelligent. And our view on this is that we are in some kind of the fourth material revolution as well. That could be 1.0, could be very, very long time ago when the humans start to discover materials and use this kind of empirical science. Then beginning of 19th century, materials 2.0, then we start to systematic do materials research using experiment, testing, validation, and so on. Also understand the physics and chemistry of the materials, and also start to understand these laws of thermodynamics. Then 1970s, we have this material 3.0, and then when computational materials science started, that has of course evolved a lot during the last 50 years. And then today we are what we call material 4.0, when it's more about big data-driven science, multiscale modeling, visual manufacturing, and this is called digital twin, and so on. So you can see in many different kind of information about this Industry 4.0 that it consists of 9 pillars, and I just want to show these pictures, and I have highlighted this big data pillar and also additive manufacturing and simulation. to highlight that data are primary resources for materials 4.0 to work. And what kind of materials data do we need? That could be a lot of different data. Could be thermal properties, chemical properties, mechanical properties, magnetic properties, manufacturing properties, of course, electrical properties, acoustic properties, and so on. And we cannot, of course, predict all of these properties, but we can predict some of them, of course. And we have concluded that processing will influence the properties, but there is also a composition dependency, of course. If you take, for example, this titanium alloy as an example, you can see in the table that the composition is actually allowed to vary within certain limits and still be classified as this alloy. This is quite common on specification sheets on commercial alloys. But however, the properties of these individual variants will differ, as seen in this plot that's showing the sensitivity of a transition temperature, the beta transus. That's actually the temperature where beta transforms to alpha, which is, of course, is important for the processing, so to decide which temperature. So when design materials, it's important to design materials that are not too sensitive and thus possible to manufacture in an easy way. So even in this specific alloy, we will have variances. So we can create a lot of different alloys from these commercial alloys, so to say. And when working with the materials design, you have a lot of potential combinations of alloys depending on the alloy composition. So for example, if we consider a system of two elements, A and B, and then we can divide the space in 10 steps, then we get 11 possible combination of A and B. And if we make the grid even finer and divide in 100 steps, we will have 101 possible combinations. So for a commercial alloy, for example, with 10 elements and 100 steps, we will have 1E12 possible combinations. And then if we take all the element in our nickel database, for example, we will have one up E27 combinations. And these are so big numbers that it's hard to understand. I mean, if you relate, our university has existed for less than 10 up raised up to 18 seconds. So from this, we can actually conclude that our design space is more or less unlimited, and only an infinity small fraction of that possible composition space has been explored today. And in order to have a chance to efficiently explore this more, we need tools, of course, such as simulation tools. So here is an example for the same alloy, but it has been following two different processing routes. The left one is SLM, and the right one is a wrought material. So we can clearly see that the resulting microstructure are different, and the phases present in the microstructure are even different in the two cases as well. And of course, the stress strain diagram to the right proves that indeed the resulting properties are different as well. So if we consider the composition, process, structure, properties, performance chain, then we need to realize that for a given composition, we have multiple options depending on what process route we select. So we can have that in mind. So I just want to give some definition of this, what we call digital twins. So actually the Fraunhofer Institute in Germany states that to ensure the digital networking of production systems and the optimization of material-specific requirements, we need to measure, analyze, and replicate the changes in material properties in a process in which digital twins of materials are created. So that's the definition of it. And to achieve this, we need to understand the process structure property relationship of materials, which we actually also relates to integrated computational materials engineering. Oops. So coming back to this Venn diagram, so in order to design materials that satisfy a specific performance criteria, then we need to be able to predict for a given recipe, and the recipe is composition and the processing, what structure will result, as well as the properties that this structure will give rise to. So to describe these links between structure, properties, recipe, performance, we need models. But all models also need data, so this is needed too. That's why data play an important role. And we have a materials data challenge. In the materials field, we have a challenge in that we don't have as much data as we would like to. In other words, we typically have small amounts of data and not big data. And traditional data sources are experiments that are costly, time-consuming, and we need new experiments for each new material or novel process to be able to use experiments. We also have handbooks. Handbooks contains limited amount of data and no data for new alloys or novel process. So these sources have limited use for design of new materials. An alternative data source could be repositories that contains more data, but still only for existing or known materials. And in order to design new materials, we need processing and analysis of existing data. And this is achieved by phenomenological and statistical models, regression analysis or machine learning, but also through engineering calculation, including mechanistic models. And by this, we can make the data more useful and valuable. So the methodology we are using for our tools are the so-called CALFAD method, which is a phenomenological approach based on describing the properties of the fundamental building blocks of materials, the phases. So it's an efficient way of integrating various pieces of information of quite different character into coherent and useful form. You kind of process the data you have and building up a model, so you actually describe the Gibbs energy of each individual phase and how that depends on composition, temperature, and pressure. And then you can extend far beyond traditional thermochemistry, and you can apply it to real engineering materials. It's also an extended methodology. We have used this method to also predict other properties than Gibbs energy. We use the same kind of methodology to also simulate volume, viscosity, surface tension, atomic mobility, thermal conductivity, electrical resistivity, and elastic properties. And it's the CALFAD methodology is a bottom-up approach, and with that we mean that you do it for pure elements, binary systems, and ternary subsystems, and then you extrapolate up to multi-component systems, you do validation against commercial data, and then you can use it for real engineering applications. And I talked a little bit about this already. So based on this alpha data, we can take it even further to predict physical properties using physics-based models. Examples, what we have today is yield strength and hardness. And I also mentioned before that using programming interfaces of Python, a user can add their own property models into this framework. So this is just a summary of a lot of different properties that you actually can predict today, and also what kind of materials you can apply them for. You can see for steel, nickel alloys, aluminum, magnesium, copper, titanium, noble alloys, and so on. So these are phase equilibrium data. I will not read all of them. You can see it yourself. And we also have physical properties, and that could be like enthalpies and interface energies and so on. But lately we have also worked a lot with thermal conductivity, resistivity, diffusivity, and electrical resistivity and conductivity, for example, and also viscosity of liquid and surface tension of liquid. And today we actually have them for most of our bigger databases. It could also be kinetic coefficients, for example. Other properties could be mechanical properties, yield strength and hardness. It could also be non-equilibrium solidification properties. That could be very important for additive manufacturing, for example. We also have the steel model library where you can predict get a lot of data from martensite, perlite, bainite transformations. And the process metallurgy module, you can optimize slag chemistries and simulate the steel refining processes. The diffusion module DICTRA, I will not go through what you can do again, but you have a lot of data that you can generate using that module as well. And this, the same is applicable for the precipitation model TC Prisma. So as mentioned in the beginning, materials are complex hierarchic system, and it's necessary to do multiscale modeling, and CalFAD actually provide a bridge between atoms and microstructure. So when generating a CalFAD database, could be both thermodynamic, kinetic, thermophysical, and mechanical. Not only experimental data is used, but also quantum mechanical calculations, DFT, are used as input data. So CalFAD data is then used to predict the evolution of microstructure using different approaches. It could be phase field or Lange-Schwarz simulation. And this result can in turn be used as input in FEM simulations as well. And CalFAD data can also be used directly as an input to FEM simulations. And in this slide, I will show that our platform provides a lot of data, models, and interactivity to support integrated computational materials engineering, developing digital twins of product processes and more. Some examples are listed here. It could be the so-called process structure and structure property models for ICME and optimization of materials composition and processes based on desired materials properties. It could also be providing material for other applications such as FEM or computational fluid dynamics simulations. It could be used for high throughput calculations for material properties and processing condition. Could also be used to reinforce machine learning models. programming uses specific tools required for daily operation and scientific model development. And this interactivity is efficiently provided through the API TC Python that can easily be integrated with other commercial and open source applications, for example. I will show you an example that relates to predicting the resulting structure. So this is an aluminum scandium alloy that obtains its strength from the scandium-rich precipitates. These precipitates will nucleate, grow, and eventually coarsen during the aging step. So we can see this from the micrographs as well, but also the simulation results in the figure. So it's important to be able to predict the amount of precipitates and also their size, since this relates to the strengthening of the alloy. And the generic strength model we have in Thermo-Calc today is actually a contribution of 3 different parts. We have solution strengthening models, the precipitate strengthening from several models, the standard patch hole relations. So all these in combination will generate the yield strength of the material. So back to this example. So here we can here we have taken the results from a simulated microstructure, that is amount of precipitates and their size, and then we use that as input for predicting the yield stress as function of aging time at the given temperature. Then you can see in the upper right diagram how this yield stress correspond to the experimental values. And the colored diagram at the bottom shows a prediction for the yield stress as a function of scandium content and aging temperature for a given aging time. And all these kind of simulations are quite important if you design a new material or a new process, for example. Another example could be, it was actually shown in an article published 2017. It was an application to mechanical thermal FEA modeling. So the learning is actually that each tool complements each other and improve the result in the next step of the process. So from CalFAD we can get the density, for example, specific heat, enthalpy, and so on, to feed the finite element simulations. And then the finite element simulations could give thermal gradient solidification rates for doing phase field simulations, for example. And CalFAD could also support the phase field with Gibbs energy and mobility data. Another example could be application to process modeling. So that's to get towards the digital steel plant. And here we're using the process metallurgy module inside Thermo-Calc for simulating kinetics of steelmaking and refining. So it actually it was done using the graphical interface, but then you can also use it in Python to set up a calculation where you have a model configuration of kinetic parameters, and you can use the steel plant specific data. You have probably a different kind of materials composition for that kind of steel process. Then you can do time stepping, material addition amount, and connect that to the level 2 system from the steel plant. And then you can take decision on the process optimization steps that is necessary. So it's a kind of an online digital twin of steelmaking process. Lately, it has been a lot of attention to machine learning, but it's worth to emphasize that this is a broad term, and this technique relies on data that is not always available. But we see a combination of machine learning and CalFAD is an interesting trend that I predict will become an important will become important for future design of materials. So in this article from 2019 from Chen et al., they actually used CalFAD calculations to improve the machine learning training algorithms. I will jump over these and go directly to my summary. Some materials are complex hierarchic systems, and their structure at many different scales, of course, determines the resulting properties and eventually the performance of the materials. And I also think that our design space is almost unlimited. We haven't stopped developing new materials, that's for sure. And we also need new materials for high demand applications for the future. So in order to stand a chance to efficiently explore this design space, then we need models, tools, and data that can predict the influence from composition and processing on structure, but also the link between the structure and resulting properties, of course. And I believe that CalFAD provides a robust framework that integrates experimental and theoretical data that extends to multi-component systems, which can be used for this, of course. Yeah, I think I end there. Thank you very much. If you have any question, I will try to answer them.
Hello. Thank you, Johan, for a wonderful talk. It's very interesting to see how Thermo-Calc and the CalFAD was developing through all these years. And we all remember where we were and where we are now. This is really exciting, isn't it?
Yes, I agree.
Yeah, I think about 10 years ago, we hardly could think about this. But hopefully this will move forward. Any question from the audience? I don't see at the moment.
May I ask a question?
Yes, please.
So I saw that there are a lot of databases within Thermo-Calc, and I wonder what are the structure of its databases. Maybe it's graph databases or some relational kinds of them. So could you discover in more detail that point?
I'm not sure I fully understand your question. Do you mean what is included?
What kind of database management system inside Thermo-Calc?
Aha. I mean, these databases are actually they include parameters that describes the Gibbs energies of individual phases, and also parameters that feeds how to say the models itself are in Thermo-Calc, the calculation engine, and then the models contain a different kind of parameters, and all these parameters are stored in these databases, and those parameters are actually adjusted using experimental and theoretical data. So it's kind of a data mining, and then they are stored in these databases.
But in what kind? Is it a relational table or something other data structure?
It's kind of tables. But
it's your proprietary technology, how you store this data?
Not really. I mean, you can use your own databases using Thermo-Calc if you have the knowledge how to do this kind of thermodynamic assessments, and those data sets are open in the literature. If you Google for the CalFAD journal, for example, you will probably find some databases there that are open, and then you can see the structure in the databases.
Okay, thank you.
I think Johan, sorry, I think I should comment about it a bit, because mathematic people understand the databases a bit differently than we do. I think Johan is speaking at the moment about the Calford type databases, and they consist of the chip's energy functions which contain parameters. And our idea is to describe properties, remaining properties, depending on temperature composition and pressure. So this is described by the function. Then you can run a calculation, and the output of the calculation could be presented in form of a table, which is more common for the mathematical, for the use of those who work in a big data. But in order to get this data, you need to run the calculation in between. And
okay, I get it.
Yeah, it makes no sense for us to have storages of results of the calculation, just because the calculation itself runs very quickly. And it doesn't take lots of power, the computer power, it's just very quick. It's several seconds with usual personal computer. And it gives you, and you can every time decide what kind of step you need. What is the size of a step of a calculation? So that is kind of, you can vary it, and you can vary the region of the calculation. Did I answer your question?
Yeah, fully. Thank you very much.
Okay, some more questions? Okay, thank you, Johan, very much.
Thank you.
I hope Thermo-Calc will develop further, and we will have new updates very soon in the program.